Good morning. This is the fifth in our series, or fourth in our series for irrigation management seminars. Today we will be talking about irrigation energy and efficiency, and basically a hodgepodge of different things that we can do to save energy and water and improve our efficiency of our system. So we've already talked about why we irrigate. To reduce risks, we can increase crop yield and yields and quality. Basically, most of the irrigation is done on high-value crops, fruits and vegetables here in Wisconsin. Irrigation is a large user of water in the U.S. 80% of the water based on 16% of the harvested cropland. So it's a large portion of the water is going to irrigation. And that's brought about some concerns because of lowering water tables, drying up of lakes and streams, and this, in Wisconsin, that's been particularly an issue that's come to forefront in the last few years in the Central Sands region. And this has led to increased regulations, whether it's pumping or reporting or getting a well put in. So one of the things we want to do is try to reduce our water usage. So one of the questions, kind of go back and see how much you remember from our first couple lectures, is how much water is required to apply 1 inch of water to an acre of land. So I'll give you a couple seconds to think about that. And it turns out to be about 30,000 gallons. And that's something that people have a hard time understanding. So that 30,000 gallons would be enough in a hot summer day or stretch when we've got ETs in the 0.25 range. That's only enough for 4 days of irrigation or plant water use. So this would be about 4 to 5 summer loads tankers of water. So in 2012, when we had the drought down the southern part of the state, there were lots of people trying to figure out how they could get water to their crops. And unless you got plumbing involved or piping already in a well, it was really hard to do. There just weren't many options. So we've already also talked about the amount of water we need. In Wisconsin, it's about 0.3 is what the crop's going to use. We're going to lose a little bit during the application. And what we usually end up designing our systems at is about 0.35. Now, if we were in Nebraska, for instance, they have higher ETs because of lower relative humidities and higher temperatures in some cases. And that also leads to higher low humidities, and wind will lead to lower application efficiencies. So they're up actually quite a bit more than us on a typical summer day. Now, one thing that 2012 taught us is that we probably can do some deficit irrigation where we hold off giving the plants all the water they might need to be out of stress until a certain point. And then at that point, we need to provide enough water. So that was a particular case in 2012. And some plants, what you get is like corn. When it goes into silk, that's a critical stage. So in my case, I had some corn growing on my farm. It got water just about the time it started silking. What was across the road, went into silk about 10 days earlier. It was about half the crop of the one that got rain at timely thing. Both were in drought stress for much of June and July, but when it went into silk, that was a critical stage, and we got water. So that's one irrigation opportunity, is do deficit irrigation, and at some point we'll get some more information and try to bring that either in a fact sheet or a webinar. So some of the options we have for saving water and energy is irrigation scheduling. So idea is to only water when it's necessary. We can lower pressures in the system. That can affect pipeline design depending on how we do that. Well and pump tests that can ensure that we've got an efficient pumping system, reducing energy. We can, some crops go to off-peak electric use, which could save us some money, not necessarily energy. And then there's variable speed pumps that can save us some energy, especially if we have one well and multiple systems, or sometimes if we're using end guns or corner systems, that can increase our uniformity. So those are some of the systems, and we're going to talk about how to find some of the issues in this as well. So irrigation efficiency or water management, sorry. So we want to make sure we've got adequate water to the crop, and as I said, there's critical stages. So the best way to do that is to use ET values and a checkbook method to track that, along with soil moisture sensors to make sure that our checkbook is accurate. And one of the questions that came in this week was the fact that since our soil moisture sensors are variable, they're if you try different sensors, they're not all the same. How do you know which one to pick or what number to pick? And my point is, everything is variable. ET is variable. Our number that we're getting to use for field capacity is a variable. And what we're going to have to do is tweak this in to get an accurate system. And it may take us a year or so to do that. So one of the things we can do is when we have had a soaking rain, 24 hours after a soaking rain, if we read a soil moisture sensor, we know that's at field capacity. So that's one point we can look at. Then if you track your, use your checkbook method and track and say that your checkbook method says that you should be at 50% soil moisture, but when you look at your soil moisture sensor, it's saying maybe you're 65%, then you know that possibly your field capacity number that you put into the tool isn't quite what your soil actually is. So you may have to tweak some of those numbers to make things work out in the end. And it works better with some soil moisture sensors than others. So like a tensiometer or a watermark sensor, you've got to refer to a chart, and it's kind of crude so it gives you a relative number in that case. If you use something like a TDR probe, that's going to list you, or a capacitance sensor, that's going to give you an actual percent moisture content. So that's a little more of a number that you can rely on to put into the tool. In all cases, why we do checkbook method is research has shown that in many cases we can reduce our water applications by 1 to 2 irrigation events per year. So that's a water saving and an energy saving. So that's one reason to spend the money on it. And I'm going to, a little bit, we'll talk about the amount of money you'd save in some cases. So one of the options here is to reduce system pressure. So if we reduce system pressure, we're going to reduce the energy requirement. Now when we do that, we're not talking about, it's the same water flow. We're talking about the same, or actually sometimes more water flow, and I'll show you how that affects. So reducing system pressure or doing something to system pressure will affect pumping characteristics. It'll affect the nozzle package you want to use. It affects the throw distance, and depending on what we do, it can affect the pipe friction loss numbers, and can increase it or decrease it depending on what we do. So here's kind of give you a cost per inch of water. So this is based on 4 gallons of diesel fuel. So we're a little lower than that, but this gives you a relative number. So this one was from Nebraska. Bill Krantz put this together, slide together. So we've got 200-foot pumping depth, and if we come up at 60, this is our pressure here, these diagonal lines. So at 60 psi, if we follow this over, we're about $2,000 of the cost to put an inch of water on. So, you know, typically in Wisconsin, we're in sandy soils, we irrigate, we're going to probably put on about 7/10 of an inch of water. You know, so we could save $1,500 just on eliminating one water event. So if we can reduce the pressure down to 20 psi, we'd reduce that per inch water cost to about $14.50. So there's a pretty good energy savings there by reducing that, and that's every irrigation event would see that. So in Wisconsin, our average water pumping depth is probably about 90 to 100 feet. Central Sand, it's much lower than that, but just on a general average. So we can save about 7% energy costs for every 10 psi of reduction. Or if we did a 30 psi reduction, so we went from 80, say, down to 50, we'd save about 23 horsepower or 17 kilowatt of power requirement to drive that pump. So that's a saving that will translate into energy savings, and we'll show you how in a minute. So when we reduce the pressure, that reduces the throw distance. So this is an illustration. So if we've got a radius of throw of 48 feet with 60 psi, reduce it to 40 psi, that changes to 44 feet. So that may not be much for this particular example, but it can be depending on the type of nozzle package or sprinkler package you choose. So to kind of illustrate this, if the throw distance is reduced, so here we go on the big circles, that was supposed to, represent 100-foot diameter, so an impact sprinkler, and we went to a lower pressure, that's going to not throw it as far, so we're going to have to do closer nozzle spacing. It's going to be the same amount of water, so we're going to have a higher application rate, so our inches per hour are going to increase. So we're going to have more water going on a smaller area. So how low can we go? Well, it's going to depend on the type of nozzle package that we choose. So if it's spray or spinners, we go down to 10 to 15 psi at the nozzle. For impacts, it needs a little higher, 20 to 30 psi. It's going to depend on the soil type and topography as to how low we can go. So here, just to kind of give you a relative number, so if we have a nozzle that covers 40-foot nozzle diameter, at 500 feet out, so from the center going out to about 500 feet, we use that as a relative water flow of 1. Out at the end of the pivot, it'd be almost 2.5 times that amount of water. So the area we're most concerned about is at the outer diameter of the pivot, because that's going to be where the highest water flow is and the biggest potential chance for erosion or water movement in general. So the output of the nozzle is going to increase as the distance from the pivot increases. So here's to show you the kind of application rates. So the bottom line here is high pressure nozzles or high pressure impact. So one of the things to look at here is this graph on the bottom, this hours, represents a point in the field. So if I have a point in the field and the irrigation pivot's going past it, it's going to, with a high pressure impact, it's going to take an hour and a quarter to pass that one spot. If I reduce my pressure down to medium pressure, which might be 50 psi, it's going to take, about 8.5, almost 9/10 of an hour. So 55 minutes or so. I go down to low pressure impact, now I'm down to 0.6 of an hour. So what's that, about 40 minutes. If I go down to a low pressure spray nozzle, I can be down as low as 18 minutes to cover that same amount of area. So that increases my application rate from about 1 inch an hour to about 4.5 inches an hour. So it's important that we have, if we're looking at that, we also have to look at the infiltration curve of that, or the intake curve of that soil type. So this tries to illustrate the potential runoff. So if we're medium pressure, it could be 28% runoff, low pressure 37%, and that spray nozzle could be 54% runoff. Now that's what's going to sit on top of the ground, and it's going to take time to soak in. So that can be a problem depending on the topography of the field. And it's also going to depend on the spray pattern. So something like a spray head, it has a donut-shaped water pattern. So it's going to be more of an issue than, say, something like a spinner that puts the water out more evenly. So here's a chart that shows the operating pressure of different types of nozzles. I don't have impacts on here, but and the spray or the throw diameter. So you can see that spinners have pretty good distance on them compared to something like a spray head. But there's reasons for using some of these different ones, and sometimes it has to do with how gentle it drops on air. So if you're doing like leaf lettuce, a spinner might not be as good as a spray head because the spinner may knock the lettuce down versus a spray head would be very gentle. So those are some of the things that we have to take into account. The spray head has a donut-shaped pattern, so if we look at uniformity, it's sort of poor. However, if we look at the center pivot is moving all the time, we get uniform coverage over time as the pivot moves around the circle. The other is wind, how different types, how wind affects different types of spray nozzles or patterns. So you can see a spray head is poor. The rest of these are pretty good. So how does it affect our pumping? So here we have this one set up for 800 gallons a minute at 300 feet of head. And the question is, what happens if I reduce the pressure by 30 psi or 70 feet of head? Well, that's going to drop my pressure, and what's going to happen if I do nothing to the pump, it's going to now operate over here. So that's going to operate at about 1,100 gallons per minute. So this poses some issues. So one is that it's going to require more head height, water column height above the intake of the pump. So my net positive suction head requirement is going to be higher. It's also going to take more energy, or more power, I should say, not necessarily more energy, more power to operate that pump. So that can be a factor. So, but it will save energy in the end, and we'll explain here in a little bit. So one of the issues is whether to modify the pump or not. So if I modify the pump, the biggest deterrent is it costs money. But if I do it, it lowers my demand rate. So I'd get that 17 kilowatt savings of energy. Now the one thing nice about a motor is I don't necessarily have to put a different motor in. If I reduce my demand, the amount of energy that the motor requires to run will also reduce. Although it may, if it's below 50% of load, it may reduce the efficiency of that motor, so it may not be as efficient operating, but it generally will save energy by doing that. The other option is to allow the pump to run in a higher capacity. So let it run at 1,100 gallons a minute. What we have to make sure is that the well has enough capacity to supply the water to the pump, and that the infiltration rate or runoff is not an issue, is that? The trade-off here is it makes us more drought resistant because I can put the water on faster. But if the water is going through the pipe faster, that could increase friction losses. So we have to look at to make sure we have adequate pipe sizing, and it can throw off the efficiency of the pump. So for instance, this previous one, we were operating in 86% efficient range, but when I drop this down, it's running at 80% efficient range. That's still a very good range. Anything above 75% is considered very good for a deep turbine pump. Higher pumping rates also, as I said, lets us use off-peak electric rates more because I can get the water on faster. And basically where I'm going to save money, it runs less hours operation to get the same amount of water on. So that's my savings. So how does the velocity of the water going through the pipe affect? When we get above, so here's about 7.5 feet per second. When I get above 7.5 feet per second, my energy requirement increases rapidly. So I need to keep my velocity of the water in the pipe below 7.5. Typically they're designed at 5, but you know, if you make a change to it, it may increase that velocity. So as the velocity goes up, the friction losses also increase in the pipe. So keeping it below 7.5 is an advantage in that regard. So how low can we go? Most systems can go to a medium pressure, so about 50 psi, which if you're at high pressure now, you're going to save about 15 to 20%. And in Wisconsin, there's actually very few systems left out there that are at high pressure, but there are still some. And depending on the topography, there may be good reasons to keep running that at high pressure because of erosion and runoff having to do with that high application rate if you lower the pressure too much. Things we need to consider is the topography of land. If it's rolling land, that could be a factor. And we may require the use of pressure regulators to get uniform application if we have rolling land. The other is the type of soil. Typically in Wisconsin we're doing sandy soils, but if you're on a clay or maybe a clay loam soil, those are going to have lower infiltration rates and a higher risk for erosion. So that's can be a factor. Now, the type of crop has a big effect on that too, because if I have grass cover that's got good roots and it may hold the soil and be able to withstand that higher application rate rather than row crops. Now, one of the things we can do on is to modify the surface of the soil. So in the upper picture here, it's showing a picture of what we call a dammer diker. It's got a big paddle that makes these little depressions that will hold the water when I'm irrigating. So what we're showing here, this is a drip or a bubbler or a drag line system. These are actually, when they do this kind of system, the rows are actually planted in a circle around the pivot. And we've got here as the water fills in here, and it allows it time to percolate in without running off. Here's another option where they've got a device that makes divots to hold the water to do the same kind of thing. So with a dammer diker or reservoir tillage is what they call it, you can hold about 3/4 of an inch of water on the surface. Basin tillage, which would make a little bigger dike, would be about a little over an inch versus a subsoil or a field cultivator. Now, one of the issues that people don't like to use these sometimes is if I come back over this and have to do a tillage event and I have to drive in this is a bumpy ride for the operator. Now, there are some companies that have come out with these that make this little dam at an angle versus straight across, so it lessens that bumpy ride. But still could be an issue, but is a way to try to store more water. So next we're going to talk about testing of irrigation pumps. So the way we test them doesn't matter on the type of pump, but just to show you. So with a deep well turbine pump, when it's on, water is going to be coming up and out. And one of the things we want to make to ensure is, one, that the well can supply enough water coming in, and that we have enough height between. So when this water is pumping, this static water, when it's pumping, this is going to be somewhat less. So we want to make sure that this height is greater than the net positive suction requirement so that we prevent cavitation. So that's an important factor. So we can test for that in doing a well test. There have been a number of studies out there, because one of the reasons to do a well test is also to try to figure out if the pump is running efficiently, as well as whether the well can supply the water. So almost every test that's ever been done, we find that there are systems out there that aren't up to standard. So whether it's Wisconsin, Kansas, Nebraska, we find that all of them have issues with systems, and sometimes the factor here why we don't fix these is because the cost of pulling the pump is greater than the savings we get from fixing them. Now, in some cases, by doing that, by finding out that they're low efficiency, we may find that we can just do some adjustments. So we can adjust the pump or tune the engine or motor, and sometimes those repairs can be done on the surface and don't require the pump to be pulled. So the Nebraska study found that 50% or 57% just need some adjustment and stuff, and they save 14% energy costs. So that can be a factor. Now, one way to do this without having a test is there's a publication out there from Kansas State by Danny Rogers and Richard Black that actually you can look at your energy bills, and with some other information you can rough out what the efficiency of your system is. So that's, if you want interested in that, you can go to that publication and run through those calculations. In many cases, we're going to do an actual well test or a pumping test. This can be done by a contractor, or if you got the right equipment, you can do it yourself. Typically, it's an open flow test, but it can be done with a pivot running as well. So what we're going to determine is if the well or if the pump and the well are meeting the design specifications. So we're going to run a test. We're going to look at the gallons a minute. We'll look at the dynamic feet of head or dynamic total head, and see if it compares to when the pump was put in or when it was designed. We're also going to look at the drawdown level at a range of pumping levels and make sure that the net positive suction head requirement is met. I had a neighbor who had a pump that wasn't low enough, and basically what happens if they're not low enough, they start surging water, or they'll start cavitating. So you're just sucking air basically. So that can be an issue. So what we're going to do is we're going to run this test. We're going to record the energy usage, and then we can calculate the energy efficiency and compare it to the pump curves and figure out the efficiency. So this is recommended every 2 to 3 years. Typical cost is $200 to $500. And there's a very nice video that Tom Shearer did from North Dakota State. It's about a 15-minute video if you want to review that on how to do one of these tests. So it doesn't matter if it's electric or diesel. Diesel is a little more complicated because you've got to bring in some fuel and weigh it to get an accurate amount of fuel used, but both can be done and calculate out that energy efficiency. The poor pumping performance can be a factor of wear on the impeller or seals, and we're going to talk a little bit about how they can adjust those, because that can be adjusted. We're basically going to look at pumping conditions like water levels and plug screens and stuff. So if it's not, the well's not supplying enough water, it could be a plug screen. So if we looked at the drawdown between when the pump was put in and how we're using it now, you may find that the water's not coming in as fast. So that could be a problem with plug screens. And that's an issue with having that insufficient net positive suction head requirement. So with motors and engines, sometimes it can be a repair or adjustment. Sometimes they're improperly sized. So it may have been put in for a high pressure system, but now we're running at low pressure, and it just doesn't meet the requirement anymore. Or we may have put in a different type of irrigation system. So sometimes they don't meet the needs, and they need to be changed, or at least we need to know that they're not running efficiently, so that when the opportunity arises, we can take that in consideration if we're doing a major maintenance requirement. The other thing is look at the gear head. They require lubrication, and sometimes they're mismatched for the engine or pump selection. So that's something to consider. And then there's the pump selection itself. So here's a pictorial of how that the water is going to run up through here. Typically, this is the spinning part here from a shaft coming down from the motor on top, and you've got a spot right here that's basically a seal surface. And what happens when that wears? These impellers on the bottom thin out, and we get leakage that basically comes around here and leaks through. So sometimes what we can do is just adjust the height of that shaft, and that moves this whole, the yellow part down closer to the casting or housing to seal this up a little bit to improve the efficiency. So that's a temporary fix, but can save a few bucks in energy costs. So when we're doing pumping plant efficiencies, we can look at the criteria. So it's the amount of energy added to the water. So in this case, it's the water use rate. So it's water horsepower per gallon per hour. So in this case, it'd be 12.5 water horsepower per gallon per hour of energy use. And if you look at so this is what's added to the water. This is water. If we look at the brake horsepower, that's over here. And if you look at the difference between these two numbers, it's 75%. So this is what's considered good for a deep well turbine pump, and that's based on the pumping plant performance criteria, which was developed by University of Nebraska. So it depends on the type of fuel as to what these numbers end up being, but we can use that as part of our analysis. So in overall efficiency, so you're going to see that the electric motor is the most efficient versus the other type of fuels, but that's mainly because electric is a secondary fuel. Actually, the conversion from coal or natural gas or whatever to electric is only about 30, 35, maybe 40% efficient at the most. But so you have to look at the type of fuel and the type of device you're running at to see what that total efficiency is. So these give you some ideas of the overall efficiency depending on the fuel source. So they're not really very efficient in some ways from the overall energy standpoint. Variable speed drives, they can help us. We can basically regulate the pump speed to maintain a pressure. This can be done manually or automatically. If we do it automatically, we're going to use a pressure sensor in the to feedback to the controller. So if the pressure goes low, it speeds up the pump. If the pressure goes high, it slows down the pump to maintain the set point. This is particularly useful on irrigation systems where we have multiple systems on one well. So in most cases, when we do that, they're not going to operate at the same pressure, but with a variable speed drive, we can we can make that happen, and in the process we can save energy. The other is we can reduce spoking or ununiform application of water because of changes in pressures from end guns and corner systems turning on and off. So that's possible. So here's the two systems. So we got two systems in one well. So the black circle here, that's my well. So in this case, with center pivot A, we've got a 50-foot distance, and I've only got a 2.25 or 2.5 psi drop versus 2,000 feet between the two pivots, and I got a 30 psi drop. So what's going to happen is that A is going to run at high pressure and B is going to run at medium pressure based on 80 psi. If I have excuse me, if I have a variable speed drive, I can force them both to operate at 50 psi so that I gain medium pressure on both systems. Or I could make one run at low pressure and one at high pressure, depending on maybe the crop that's being used. Here's an example of spoking. So these are aerial pictures. So you can see these pie-shaped pieces here indicates more water or less water on the system. Now, you're going to see it change as we go around here, and that's basically to do with time because it takes these systems 2 days to go around in a circle, typically. The other thing that these pictures may not, it may be changes in pressure, but it also could be slippage of a wheel. So if muddy conditions, that can also cause issues. So it could be variable soil types within a field that can cause some of these conditions as well. Next, we want to cover irrigation efficiencies, the types of efficiencies. So the first one is conveyance efficiency. So that's getting water from the source to the field. And in Wisconsin, that's typically piped in. Maybe there's some channeled in, canaled in that might be for cranberry growers, but for most of our crops, it's going to be piped in. So typically, especially when you have a well, you'd consider that 100% efficiency, but it depends on the system. If we're using a reservoir as a surge container, that may be less than that. The next one is application water efficiency. So this is the amount of water delivered to the field versus what can be used by the crop. So the big thing is what's lost as far as wind and evaporation losses. Here in Wisconsin, because of our higher humidities and lower wind in general, we typically have maybe 5% loss, up to 10% loss, versus if you look down in Nebraska, it could be 15 to 20% in some cases, because sometimes they're running relative humidities in the 25% range versus ours. We do get a few of those days, but not many in a year. The exception was 2012 when we had a series of those, or at least late afternoon, we would often get in those low relative humidity periods. The next one is irrigation efficiency, and this looks at all uses of water. So it could be leaching of salt, it could be chemigation, cooling, frost protection. So, you know, all uses of water that might be beneficial. The next one here is water distribution efficiency, or how the degree the water is applied to the field and uniformly infiltrates into the soil. And we're going to talk a little bit how you might measure that. It's pretty timely, or takes a lot of time in general. The other would be distribution uniformity, or coefficient of uniformity, which is two different types of tests, but you actually take the data the same way, but you calculate, it's two different calculations of the same data. So one is to look at the lowest quadrant, or the lowest 25% compared to the average water applied to the field. And the coefficient of uniformity more looks at a straight average. but it's how well we've distributed that water across the field. And we're going to talk more about how that test is done. So here's an example of conveyance efficiency. So this is a pipe with a leak in it. I think that was at a coupling. So just an example that this system's not going to be 100% because we've got a leak. Application efficiency, if you want to calculate your own, it's basically if you've got some water gauges you put in the field, and you put them in different spots, and then you look at how much you collected by the gauge versus how much was delivered to the field. So if you want to know how much is delivered to the field, you probably have to have a water meter in the system, and then you'd use what was in the ring gauge to figure that out. So water delivered to the field, you can go through this formula. So it's gallons per minute times the hours applied divided by the acres will give you the inches of depth of water, and then we can collect some in a gauge, and we can calculate that as well. So here's an example. We had 800 gallons a minute for 46 hours. That was 0.62 over 130 acres, 0.62. We collected half an inch in our meters, so this works out to 81%. So that's quite a loss comparably. Here's distribution, water distribution efficiency. So this would be, we'd have to measure, use a soil moisture probe like a TDR, which is pictured here, and you'd have to make a grid pattern. So you'd have to walk the field, make a grid pattern to get a rough idea of how uniform the moisture infiltration is in that field. But the other thing you're going to pick up when you do that is you're also going to pick up different soil type variations. There is a company that makes a tow-behind device that can be doing the same thing. It's called a Varius. So that's another way to do it, is a towed-behind device that measured receptivity as you pull it across the field, or the resistance of an electric charge moving through the soil as you pull it across the field. So I want to spend a chunk of time here on this uniformity testing, because during our infield day, we hope to possibly run one of these tests so you can see how they're done. But we need to put out a line of gauges here, and we're going to collect the water, and we're going to look at how uniform the water was collected in all those gauges. So what this test checks indirectly is not the amount of the moisture in the soil, but the moisture that was applied to the soil. So, you know, every one of those gauges, we're assuming that if it made it to the gauge, it's going to make it to the ground right below. Now, whether it stays there, that's a different question. Indirectly, it's going to check sprinklers for wear, restrictions, and some sprinklers have rotation, so it will check that. It also can be used as a commissioning test on new sprinkler system that they were put in the correct order, because on occasion people put them in backwards or sections of them in backwards, so that's good to know. So it can be used as a commissioning test. The recommendation is that these be done every 3 to 5 years, and that depends on the quality of the water. So if you have water that has iron in it or something, you may want to do this a little more often to check those. But you need a lot of rain gauges or pans or something, buckets to do this in. But we've got some kits around the state that are available for free to do that. Typically, the life of a sprinkler is about 10 to 15 years, and then they wear out. Basically, the nozzles enlarge, and they need to be changed. So this test doesn't get the obvious problems. Those we can usually see. So here's one where we got a boot at the end of this or a drain valve that's not sealing properly, and here's a nozzle that may not be spinning. It may be stuck in one spot, or part of it's not working, so these are supposed to have multiple streams out, and this may only have one, so it's not working properly. So those problems we can typically see if we take time to look at the system. The not so obvious issues is something like this where we have ununiform. So you can see this is a scallop shape here with a corn. So this is probably a problem. It could be a couple things. One is the pressure is too low in the system, so the water isn't getting thrown far enough. Could be worn nozzles. It could be the nozzle spacing is too large here for what the nozzle is. Basically the improper nozzle. So it can be a number of those. So we can find that out using this test to a certain extent. And here's an example of a case where a nozzle was plugged. So we got this area that's not going to get enough water. So what are the effects of non-uniform water application? Well, the overwatering or underwatering, so that leads to plant stress. So if it's overwatering, it can lead to fungal diseases. If it's underwatering, of course, it's not going to have enough water to grow properly. And with this test, we can tell this. The first year we put these kits together and went out in the field and tried this, one of the farmers found that he was applying like 3 inches of water right around the pivot, whereas the rest of the system was very uniform. And that explained why the potato crop, when he used that for potatoes, was dying of fungal diseases. He could never figure that out. It was too wet. And we picked that up where he couldn't have seen that otherwise. If we're using chemigation and we have uneven water, that can affect our fertilizer application, herbicides, or pesticides. And it can lead to localized leaching as well. So what's the cost of poor uniformity? So if I have a problem where I have a 20% reduction in water or yield application because of poor water, and this is looking at potatoes at 350 hundredweight at $5 per hundredweight, you can see as we go out on this pivot, the cost is more because as we go out, one nozzle covers more acres. So here it's $1,000 to $2,500 just because of one nozzle in that field was not working properly. So it can be a very sizable number that this test will help identify. The other thing we can identify is basically nozzle maintenance. Poor water quality can affect uniformity, as well as the pressure variations in the soil, in the end guns and corner systems. Now, to catch that, typically when we run this test, we'll run it with the end guns either on all the time or off all the time. And then if we wanted to look at those end guns, the effect of those end guns and corner systems, we would run in the test, repeat the test again with those systems engaged. So you'd compare the two to get an accurate answer of what the effect of that is. Wind can be a factor affecting uniformity tests, both when you do the test and just affecting uniformity in general. The type of nozzle will affect how we can measure, how accurately we can measure it. And we'll talk about that here in a second. The American Society of Agricultural and Biological Engineers has a test standard for how to do this test. So typically we're going to put out rows of rain gauges or cans to catch the water. They all need to be identical. Now what we found is that most people don't either have enough cans or have enough patience to do 2 rows of tests. And you can get enough information by using 1 row of cans. And if you want to, you can run over twice to get the same results. So this is what most people use. If you put 1 row out, you run the pivot over, and you can calculate your numbers. If you want to get more accuracy, you run it one direction, then turn around and run it the other direction. And you'll find that they're usually pretty uniform. There's some variation, but they usually be pretty uniform. So this requires 1 or 2 rows of gauges or cans. We want the nozzle, the gauge or the spacing of these cans to be set up on 80% of the nozzle spacing. If they're always in the same spot between the nozzles, we're not going to see the very necessarily see the variation we're looking for. So typically with a spray nozzle, we're going to put it at about a 10-foot spacing based on the nozzle spacing. So if that's the max, or 80%. So if the spacing, say we have 10-foot spacing on a spray nozzle, we'll put those at 80% of that, which is 8 foot apart. Now, if it happens to be at an even increment, so say we had impact sprinklers that were at 32-foot spacing, which isn't odd for a high-pressure system, and the maximum for the spacing for the impact is 16, that's an even increment of 32. So we want to change that spacing. So typically I would use 80% of that, so about 12-foot spacing for that system. You can never have gauges, too many gauges or too close. It just increases the reliability of this test. And they don't necessarily have to be even increments through that, although it makes the record data entry a lot easier if you do. There also, we need a minimum height of 3.5 feet between the top of the gauge and the sprinkler. So that's basically so that when the water's coming out, it's coming down into the gauge. So if this was my cup here, not very good at that, we don't want it to come sideways into the cup. We want it to be coming down into the cup. So that's the reason for that. Then we have end guns or end sprinklers, and we can't expect them to be uniform over the whole coverage pattern. So there again, it's about 75% of the wetted radius of those systems. So if we had an 80-foot coverage wetted area, we'd use 60 foot of that in our calculations when we're doing this. So here's a picture of the systems that or the test kits that we have. They're in 3 boxes. One box is cups, and the other 2 boxes are the stakes. The stakes you can push in the ground. They've got a little tab. You can push them in the ground as long as the ground's not terribly hard. You can push them in. You put a cup in. You got the measuring devices for spacing it out. You put a row of them out there. You got directions. There's software in this package, data sheets, everything you should need to do this. And we have one in Hancock Research Station. There's one in Rock County at the Extension Office, and the other one I think is in Chippewa County. I haven't looked lately, but we can round that up if somebody needs that one. It's up in the northwest part. So here's what the cup is. It's 4.5-inch opening. The standard, or based on work that Kansas State has done, that needs to be 4-inch opening to be accurate, especially for spray nozzles. We've got a metal stake, and these are fairly inexpensive to make if somebody wanted to make their own system. It's just basically a piece of tubing cut off into about 1 inch or 1.5 inch length and welded to a rod. And we put a little tab on here so you can step them into the ground. And this is a 42-ounce soda cup. So here's the data we can get out. So here we've got depth collected over the distance from the center pivot. So this is going out on the center pivot. So you can see this system here that had lots of variability, and basically had a downward trend, and basically that's probably because of worn nozzles. And the coefficient of uniformity, which is kind of an average number versus the low quadrant, was about 72%. So that's not a very good number. That would be in the poor range, and we'd want that to be at least 85%, preferably about 90% for a center pivot. And it can be done. So, and these dashed lines here, these are plus or minus 10% of the average of the yield. And the test, what they do is, as you go out in here, the sample I get out here is giving more weight in that average number, so it's weighted based on the distance from the center pivot. So if I have a problem out here, this number here is going to give more weight than, say, this number here that's closer to the pivot, is the way that is calculated. And we'll go over that when we have our workshop. So here's one that's, this one is 90% efficient. Yes, there are a few high points, but you have to kind of look at the scale here compared to this one. So this one was about 0.75 inches or 0.7 inches of water and ranged up to almost double that. With this one, it was about, it looks like about 0.45, which should have been more water than that, but and yeah, it's almost double, but there's only one of these compared to the rest. But you know, as we get out here, it's actually, most of these are pretty right in the range of plus or minus 10%. We can also do this test on a solid set or movable system, and here we would just set the cups out between the sprinklers. We'd set a grid pattern. Now we can't do the whole system here, we can only spot check it. So we'd set it out. Typically we'd recommend they be no more than 10 feet apart. We'd set that pattern up and catch the water and calculate the number as basically an average number. But it can be done in this case as well as on traveling guns. So here's a traveling gun we got set up. Here's the line of cups crossed out here, and the pivot's going to move down here and fill the cups as they come by, and then we collect the numbers and do the calculations. So here's the numbers on this. So you can see this is actually, you know, this end of it's actually pretty uniform. We don't want to count these numbers here because we don't expect it to be uniform over the whole range. And we just have this side here, we've got a little blip here. You know, that might be able to be fixed with a maintenance issue, but at least we've identified it now, and we can try to see if we can improve that and then retest it and see what if we made any improvement. Off-peak electric is another thing we can do is save energy. It doesn't reduce energy usage, but it saves energy costs. So here's an example. Liant, their general service rate's 12 cents a minute. This was in 2010. Their off-peak, depending on the hours, so this is a 14-hour period, this is a 12-hour period, was about 20 to 21 cents on peak and about 5.5 cents off peak. So the more you can shift to off peak, the lower your cost is. So if you want to do this and cover a pivot to get enough water on based on a typical ET in Wisconsin, you're going to need about 1,200 gallons a minute for a straight quarter system pivot and about 1,400 gallons a minute for a straight system with a corner. So 130 acres versus about 150 acres system. This is going to be useful for deep-rooted crops. It's not going to be useful for vegetable crops in sand, just because there's not a deep enough root zone and not enough water holding capacity of those sandy soils. But you can still shift a good bit of it onto that off-peak. So here's an example of a typical system. We've got a 90-foot height, pumping height, 1,200 gallons a minute, typical efficiencies, 11 inches of water a year. So that's going to cost, if we use the general service rate, about $8,900 a year to apply that water. If we can shift most of it to off-peak electric rates, time of day use is what the TOD stands for, and maybe 20% on peak, that still saved it down to $6,200. If we can shift it all to off-peak, we're saving more than half of the cost of applying that water. So that's just an example of what we could do. The other thing we can do is fuel switching. There again, it doesn't save energy, but it might save the farmer dollars. So this is at 3 1/4, so that's kind of what it's running at now for off-road diesel fuel. And so if I could find electric for less than 23 cents a kilowatt hour, electric would be a cheaper rate, and in most cases it is. It's going to be even at my time of day use, it's going to be cheaper. So electric can be up to half the price of diesel. Natural gas is running under $1 a therm, so it would be cheaper. LP gas, well, that's about what it's running at, along with gasoline at this time. So there'd be no advantage to switching to LP or gasoline, but to natural gas or electric, there would be a fuel savings, a cost savings, not necessarily an energy savings. So how can we pay for some of these things? Because there are some incentives out there for saving energy, and in some cases for saving water. So the first one is energy. So the first person to contact is your local utility service rep. They can tell you what programs that they might have. The other place you can go is this desireusa.org. It's a database of state and federal incentives. So in some cases, there'll be some federal incentives. For instance, there's a REAP program, which I'm going to talk about next, and there may be some tax credits for saving energy. So the REAP program is the next one. This is Rural Energy for America program. This has been around, well, it's been around longer than 2008, but that was the last time it was reauthorized. Grants can be 25% of project costs. I'm not going to go through these, but it's grants or guaranteed loans. They're not for mobile equipment, so it can't be for buying a new tractor to run my irrigation pump, but it could be for updating the pump. If it's a stationary unit that's dedicated to the irrigation pump, that would probably qualify. But you can go, this is run by the Rural Development Agency of USDA, which is in Wisconsin, located in Stevens Point. And Brenda is the person, she is the person to contact on that. And you can get all kinds of information about it at this website. The other website that's helpful is this farmenergy.org. They've got some templates and stuff that may be handy for doing these programs. The other programs are NRCS equipped programs. So Scott Mueller from the state office sent me these yesterday. So we've got a water management plan, so we can plan out. And this is, all these programs are basically to conserve water, to reduce contamination, to reduce energy use, reduce erosion runoff. So that's kind of where they're aimed at. So I'm not going to go through the particulars, but they're written down here on the slide. And if you Google those, you probably can find the bulletin on those. If you need help, holler, and I can send you a link to them. But so the first one's a CAP 118 water management plan. Next two, we've got a sprinkler irrigation system. Basically, it's trying to look at uniformity of water application. And so this one here, I'm pretty sure is the one that would require a uniformity test. So you have to do one when you get under the program, and if you find some problems, you're supposed to try to correct those problems and then run the uniformity to increase the efficiency. So this program in the past there's enough dollars in there to basically pay for the test and pay for a new sprinkler package. And in some cases, your irrigation contractor may do it as a service, maybe even a free service if you buy the sprinkler package. That's one place to do it. The other is a water management plan. So this is basically water management, checkbook, use of soil moisture sensors to make sure that you're not watering unless the plant needs it. So this is looking at, trying to look at reducing infiltration, or not reducing leaching in the groundwater and surface water, and basically optimizing the use of water. Another one is pipeline, irrigation pipeline. This is 430. So this has to do with conveyance of water system. I'm not sure how much that would be used here in Wisconsin, since majority of our systems are in piping, but there may be some cases where it does have an energy component to it. So if piping was grossly undersized, that might be a place that could be used. And then NRCS is trying to push micro-irrigation, or trickle or drip irrigation, which we're going to talk about next week. And again, to reduce contamination, uniform or efficient use of water, many microsystems can reduce water usage by half of what you'd use in a sprinkler system. And in the process, it'll reduce energy. So those are 5 other programs that may or may not be useful to a grower. Here's a list of resources. One of the 2 that we've already talked about in the past, I think John highlighted these, is these are a couple new publications that you can find at the Learning Store. This Kansas State Mobile Irrigation Lab has a lot of good publications and stuff. Nebraska's got some nice stuff, and then the NRCS has some stuff. And this one down here, this online bulletin, this will cover quite a bit of the stuff we've talked about throughout this whole series, but in a written form. So you can go online and look at that if you want. So with that concludes our program for today. So we'll stop the recording and we'll take some questions. And if you're viewing this after the fact of the live presentation, you can email me the questions and we'll try to get you answered.